In this lecture, we're going to talk about liquid chromatography. This is chapters 8 and 9 in the BioSeparations textbook. So let's look at chromatography. Chromatography is, at least at a capillary level, let's talk in the simplest possible terms. Chromatography is essentially flow through a pipe. Okay, so if we were to have a pipe, and we're looking at a pipe cross-section here, let me take a slice through that pipe and spread it out for you. So now we're looking at the longitudinal section of the pipe, or what's inside the pipe. If we were to put a bolus of something, of an analyte, in that pipe, okay, and that's denoted here in red, so we fill the pipe with something. As soon as we impose a flow inside that pipe, what would happen to that bolus of material? Well, flow in a pipe, if you remember fluid dynamics, flow in a pipe, the velocity at the wall is always defined as 0. The velocity at the center of the pipe is the maximum velocity, and it's moving faster than velocity everywhere else in that pipe. So we have this parabolic flow profile. Well, if all the fluid in the pipe is moving at that velocity, then that bolus has to deform. Okay, the material will move fastest at the center of the pipe and won't move at all if it's adjacent to the wall. So we get this classic kind of bullet shape. Now there's something else going on in that pipe, and what's going on in that pipe is diffusion. So we have diffusion from the walls out, or from the bolus, as the bolus is distorted from the center to the wall. So there's diffusion, there's radial diffusion, but there's also axial diffusion. So wherever the concentration is great inside that bullet-shaped thing, it will tend to move axially along that pipe, and it'll spread the bolus of material out into the mobile phase as the velocity down the pipe is moving things advectively. So let's look at an example.
Wait for the dye bolus to diffuse across the cross-section of the pipe. For this thin pipe, the wait time is more than 12 hours. Start the pump and camera simultaneously. Allow them both to run for 5 minutes. The images from the experiment are above the inferred concentration curves at 3 different non-dimensional times during the experiment. These data are for a thin pipe for which the ratio of short to long sides of the pipe cross-section is small. The shape of the distribution changes as the dye bolus moves downstream. The initial Gaussian-like symmetry in the longitudinal direction is quickly broken. Monte Carlo simulations with a matching initial distribution and flow rate confirm the experimental results at 2 different dimensionless times. The solid lines are experimental data, and the dashed lines are simulation results. This comparison is for a thin pipe with a small ratio of short to long sides of the cross-section. Monte Carlo simulations also provide confirmation in the case of a thick pipe, where the ratio of cross-sectional lengths is near 1. Note the difference in the evolution of the concentration between the thin and thick pipes. Over time, the thin pipe has solute with a sharp front and a tapering tail. The thick pipe has the opposite profile.
All right, so what's the model for this? And the derivation of this is in the textbook. I'm just going to show you the result of that. And what we have here is a time, radius, and distance down the pipe dependent flow. Okay, so the concentration of our analyte, of our bolus of analyte, will change as over time at any given radial and distance, or z axial position, down the pipe. So we have a transient term. We have radial diffusion, center to wall or wall to center. It can be either direction. We have axial diffusion away from the high concentration of the bolus. And then we have what is being convected by the flow rate. Now remember, the flow V sub z is the velocity in the pipe. That goes to 0 at the wall, which means the advective flow at the wall term goes to 0. but it's maximum at the center of the pipe. So we have a situation where diffusion dominates near the wall, or will probably dominate near the wall, and advective flow dominates in the center of the flow channel. Okay, let's make this dimensionless. So if we define dimensionless numbers, so we'll define eta as the dimensionless radius. So if you think about the radius starting from 0 at the center of the pipe and moving out to capital R at the wall, eta will vary between 0 and 1. Okay, if we define lambda as the distance down the pipe from the starting position of the bolus down to the end of the pipe L, z equals 0 at the starting position, and it equals L at the end of the pipe, or the end of our experiment, and that means lambda goes from 0 to 1. Okay, eta is the concentration of the analyte, and that's in the bolus. Well, we saw from the previous experiment that was done that when we first load the bolus in, that's where it has its maximum concentration. So we call the initial concentration, that's the maximum. At time equals 0, the actual concentration would equal the initial concentration, so eta sub A should be a maximum of 1. Throughout the rest of the experiment, it's declining. And where concentration goes to 0, you can't have a negative concentration, so the lower limit on eta sub A is 0. So eta sub A also goes between 0 and 1. Now, we have to deal with time, and there are actually two time scales. We talk about this in the textbook. The one that works the best is the time scale for the material to move from z equals 0 to z equals L. Okay, so that's the distance that's being traversed is L. The maximum velocity inside the pipe, you can use maximum or you could use average velocity. I tend to use maximum velocity. And the maximum velocity says that the higher the maximum velocity, the shorter the time it takes, the lower that dimensionless time constant would be, things will move down that pipe faster. Okay, so tau starts at 0 because time can go to the initial time is 0, and it can go to L over V max. All right, so if we make the appropriate substitutions in our model, what we find is the dimensionless form of the model, and we still have our temporal term, our radial diffusion term, our axial diffusion term, and our advective flow. Okay, and if we look at this number, this is dimensionless. It goes from 0 to V max. That was why I used V max. Okay, so this dimensionless ratio of velocities can go from 0 to 1. Okay. If I factor out the diffusivity, that L should be a capital L here. If I factor out the diffusivity, I have this number here, which turns out to be dimensionless. And we're going to go into this number in a minute. Now here I've got the axial diffusion term, but I've got a multiplier, a dimensionless ratio here of the outer radius, or the inner radius of the pipe, the maximum radius of the pipe, R, divided by the length. Well, if R is small compared to the length of the pipe, then this number is less than 1, and I'm squaring that number, so it's even further less than 1. So what that says really is, for most of the time when I'm dealing with small diameters and large lengths, then this axial diffusion term really becomes negligible. So we can drop that from our model, and we reduce the model to this. All right, so let's go back and return to this dimensionless number. So what is this dimensionless group? Well, it's actually the ratio of two time constants. The first of these is the diffusion time constant. So it's the radial diffusion time constant. So diffusivity is length per unit time, radius is length, so length squared. So if I have length squared per unit time divided by length squared, I have per unit time, okay, which is the time constant for diffusion in the radial direction. Okay, L over V max we've already talked about. This is the time it takes for the bolus to move, or the initial part of the bolus to go from z equals 0 to z equals L. The faster we're moving, the shorter that time. Okay, the units here, length per unit time, that puts time in the numerator. So the faster things are moving, the lower this ratio becomes, and the shorter the flow time constant is. So this dimensionless, or this is a dimensionless number because we have seconds divided by seconds. This is a dimensionless number, but it's the ratio of the time constant for flow down the pipe to diffusion from the walls of the pipe to the center. All right. So now let's think about this. If our flow time constant is very much larger than our diffusion time constant, then diffusion is faster than the flow down, than the time it takes to get down the pipe. We have a more uniform distribution in the flow channel from one edge, from radial distribution of concentration in the flow channel, but we have lower throughput because we're flowing very, very slowly down that channel. Okay, if the time constant for flow is very much less than the diffusional time constant, then we get that bullet-shaped flow. Okay, we have higher throughput, but we're leaving stuff behind, and it'll tail out kind of forever. That's left in the capillary. The stuff nearest the wall doesn't have a chance to diffuse out, so we get that long kind of bullet shape that you saw in the video. When we're in a chromatography process, what we really want to do is balance the diffusional time constant to the flow time constant to make that dimensionless number essentially equal to 1, or as close to 1 as we can get. That's where we get the best uniformity and the highest throughput. So that's our design goal in doing chromatography. Now it turns out these variables, even though we want to optimize to a value of about 1, it turns out these variables are related to one another. So it's not always possible to do that easily. First of all, we can't change the diffusivity. Yes, we can up the temperature and that will increase the diffusivity a little bit, but for practical purposes we really can't change the diffusivity of component A in mobile phase B. If you look at this number, okay, it looks like if diffusivity is constant, length is constant, if we decrease R, we should be able to increase V max. Okay, but those two are related. Ultimately, we hit a pressure drop limit for the capillary, or for the pipe that we're flowing things through, or the pump that we're pumping things through. So if R gets smaller, then V max has to get smaller if we're up against a pressure limit. If V max goes down, the volumetric flow rate goes down, which means our productivity goes down. If L is long, Vmax also has to drop for the same pressure. It's the Vmax scales as 1 over the length of the pipe. So the longer the pipe, the lower Vmax has to be. So all of these things interact a little bit, and it makes it a little bit hard to control this, to really optimize this process. So at some point, how do we maintain a high volumetric flow with the smallest possible flow channel diameter? That's really what we want to do, and this number doesn't allow us to a whole lot of leeway there. Well, let's do a little thought experiment. Okay, what if we have one capillary or one pipe that has a small r and a long L, and Vmax is fine, and we've optimized it to order 1 for that term with the diffusivity we've got. Okay, that's kind of the perfect optimum position. Okay, so if we just multiplied a number of those smaller pipes together, we welded them together, and now we've got a big group of those pipes together, we could up our volumetric flow rate by the number of pipes we put in parallel. That would be great, except R would have to be absolutely the same in each pipe in order for the flow rate to be the same through those pipes. That's a problem. Okay, there's enough variability in the manufacture that we couldn't maintain a constant enough R, and we would get differences in the flow rate through each pipe, which would broaden our peak as we go through. So that's problematic. Now, what if we do shorter lengths of pipe, okay, and we weld a bunch of pipes together and we chop it into sections and we leave a little mixing zone between each section? Well, now we're remixing the output of one pipe before we go into the next pipe, and as long as those mixing zones are negligibly small, but they allow good mixing compared to the lengths of pipe, we could obtain a separation at high throughput that way. Well, let's take that to the extreme. Okay, what's another way to churn one big flow channel into multiple flow channels that divide and mix and divide and mix? Well, an easy way to do that is to fill a pipe with beads. If you fill a pipe with beads, the interstices between the beads are like little flow channels. Okay, and then after you come around a bead, those channels can merge and mix, and then they redivide again around the next bead. And that's really what we do in chromatography. So if we look at this situation where we have a bed of beads and we're flowing stuff through it from left to right here, give this a minute to run, and you can see how a bolus of material will start to move through that bed of beads, and it moves kind of as a flow front. There's some gaps where there's a no flow zone, okay, but ultimately it comes out at the end of that. Instead of with a bullet shape, it comes out kind of uniform at the end, and that's what we do. All right, so let's continue with our capillary model, and let's get into the meat of what makes chromatography different from just flow through a pipe. And here we're going to do a material balance. This is how we got the model that we generated, was a shell balance. We go look at a delta Z region of that pipe. We look at the flux going from the center point of the pipe out to the wall. Okay, that creates a shell that we're doing this balance equation around, and we write out our balance equation. That should be familiar. This is in dimensionless form. But how many initial and boundary conditions do we need in order to solve this equation? Well, we're the first derivative with time, in this case dimensionless, but first derivative with time, so we have an initial condition that we can specify. We have two derivatives with respect to radius, so we're going to need two boundary conditions with respect to the radius, and we have one partial derivative with respect to length, so we have one boundary condition with respect to the length. So that's what we'll need in order to integrate and solve this equation as a function of time. Now, the initial condition is kind of easy. Okay, we have a bolus of material that is coming into the column, which is which is fully concentrated until it goes to distance lambda 1, okay, down the axis axially down the column. That's our bolus. Okay, this is a square wave bolus, and then it's 0 from there on. That's our initial condition for the concentration. Now, our boundary condition for length is again pretty easy. we assume that there's nothing flowing behind the bolus. It becomes zero, okay, for any time, the zero entering the capillary at lambda equals zero, it becomes zero new material entering the capillary at t greater than zero. Okay, so that's a fairly easy boundary condition. We're allowed one of those for lambda. Now, what about eta? So, what's the boundary condition for eta? Well, we're allowed two of these. We have the symmetry boundary condition at the center point in the pipe. Okay, the concentration gradient has to be zero at that center point at all time. Okay, that's called the symmetry condition. That's a given. What about the second boundary condition? Well, we normally set that at the wall. If this was simple transport down a pipe, okay, then there can be no diffusive flux through the wall. That would be the normal boundary condition for just flow through a pipe. Chromatography is different. And in chromatography, we have adsorption and desorption to the wall itself. So the component, the analyte that's moving down the capillary, can bind to the wall, take itself out of solution by binding to the wall when the concentration in the solution is high. But then once that concentration moves further down the capillary, it can desorb from that wall. Okay, the rate of mass transport drives the kinetic constant. The rate of mass transport versus diffusion drives the kinetic constant. Okay, that's K prime. And the equilibrium constant for that component to bind to the wall is really what's driving chromatography or chromatography separations. If we have component A and it has a high affinity to the wall, it's going to spend more time on the wall relative to another component that has less affinity for the wall. Okay, and because it's delayed by the presence of the wall or by its binding to the wall, it will elute later than a component that has less affinity for the wall. That is chromatography. So we've described it in terms of a single analyte, okay, and the bolus of a single analyte, but we can easily extrapolate this to multi-analyte situations. Capillary chromatography is what you get in gas chromatography. You can actually run liquid capillary chromatography as well. The wall is usually composed of something that the components will selectively bind to. So this model really does have utility for us, but only in a true capillary condition. We're going to have to modify this for the case where we have a packed column. So it's this difference where instead of no transport through the wall, we have a reversible kinetic loss to and from the wall is what defines chromatography. It's a boundary condition. Okay, so let's consider a packed chromatography column. Now, a packed column will have an average bed porosity. So think of the beads now do not allow flow. They occupy a certain volume within the column, and the volume of fluid around the beads is the average bed porosity. Okay, we have a bulk concentration of component I that's in the mobile phase, but it's diffusing through a boundary layer to and from the surface of the beads. We'll get into that in a minute. So in the pores between the beads, we have a bulk concentration, and then there's a boundary condition moving to the bead. Now we have a inlet concentration, which this is our square wave injection, so to speak. So it goes up at some time to our maximum concentration, and then once we've loaded in a bolus, it drops back down to zero. So that's our feed concentration of the component I. We have diffusivity of component I in the bulk fluid, whatever the mobile phase is. Bulk, I'm really describing the mobile phase, the solution that's going around those beads. The velocity, or instead of maximum velocity, we're talking about here the interstitial velocity through the bed of beads. This is kind of the average velocity around the beads. Remember, if we have a small gap between two beads, or interstices between beads that are packed together, it's wide. It can be wide going to small, going to wide again because of the curvature of the bead. So we can describe an average interstitial velocity through the bed in terms of the volumetric flow rate divided by the effective cross-sectional area. And then we have a radius of the spherical particle. Now, we don't deal with the radius of the column here. We really deal with the radius of a spherical particle because all of our action is occurring at the surface of the particle. This is where we have the particle, the composition of the particle, and the makeup of its surface is what defines the equilibria binding of the analyte to that surface. Okay, so think of it in terms of capillary. Our capillary is the interstitial fluid moving through the bead surfaces. The actual surface of the column we can ignore because the beads are small relative to the overall area of the pipe that they're packed into. Therefore, we can kind of ignore the surface of the column itself. All the actions occurring against a particle bead. All right, so that's just giving you an idea of what each of the variables are. If we start with a bolus of material coming in, a nice square wave bolus of material, and if you've ever run a chromatography column, you know that there's a sample loop that you load your sample into the sample loop. You then switch the flow, so the flow is always constant through the column. You immediately switch the flow so that it goes up through the sample loop and pushes that sample into the column. That gives you a very square wave bolus into the column when you do that. But as it moves through the column, okay, the material is diffusing. It's going to the bead surface, coming back off. So you're getting some broadening of that peak as it moves through the column, but you get a peak coming out that is more Gaussian in shape because of all that diffusion and all that mixing that's occurring between the beads. And you can see that you can measure that at your detector. Okay. So we have to change our mass balance a little bit because we've got a packed column, and that really comes into this term that we add in. Okay, we have our temporal change, we have our axial advective flow, we have our axial diffusion here. Okay, we've changed things a little bit because we don't have a radial diffusion component. We're going to pick that up when we talk about the bead, so let's ignore that for now. We drop that out of this equation. But what we do have here is a loss of material to the surface of the bead through that boundary layer. That's what we pick up here. And this is kind of a generation term, and we're going to have to model that, and that's where our diffusion, our quote radial diffusion, comes back in. Okay, so this is if we were talking about a catalyst bed. If you had a plug flow through a catalyst bed, for those of you who are engineers, that would be a generation term essentially. But remember, we're not losing stuff. We're losing stuff from the flow, but it's reversible. Okay, so we're not consuming something. Well, we are from the standpoint of the bulk fluid. We are consuming it to the surface, but then we're generating it back from the surface. So that's what these two concentrations are, and Cp sub I is the surface concentration of analyte I immediately adjacent to the particle surface. So this is mass transport times the concentration gradient driving that mass transport. As the bulk concentration drops, stuff comes back off the surface. We get negative generation. As the bulk concentration goes high, we get stuff moving towards the surface. Okay, so that's the major change in our model. The derivation of this is in the textbook. I'm not going to go through that. You can always get the textbook. So here let's look now at our particle of packing. And that particle has a radius. We tend to try to make the radius of these particles as even as we can in chromatography. It doesn't have to be, but we tend to do that because it makes it easier to know what the pressure drop is going to be, what the packing density is, those kinds of things. All right, so the particle has a radius, rp, and it's got a diffusional boundary layer around that radius. Okay, this is where the mass transport is occurring. Now, yes, there's a small amount where the two particles touch each other. There's a small loss of mass transport at that point of touching, but that's really pretty negligible as long as these particles are reasonably round. Those points of touching are kind of negligible, so we can ignore those for the purposes of the model. There's mass transport through the boundary layer from the bulk to the surface. Okay, the rate for that is the mass transport coefficient times the area of the particle. Now we can, if we think about the whole cross section, okay, then it's the area that's in contact with the liquid, so to speak, in the cross section. And this is our driving force, the bulk minus the surface concentration, so it can be plus or minus depending on whether the bolus is passing by or has passed by. All right, so there's a surface concentration of component I in the fluid phase adjacent to the surface. Now, particles can also have porosity. Now, the porosity does not allow bulk flow through the particle. This is pores in the particle itself. Okay, so we do this because it increases the effective surface area for binding of materials to the particle. So very often chromatography particles are highly porous, and we have to now worry about diffusion in and out of the particle pores. Now, on the outside of the particle is CPI, the concentration of the analyte I at the particle surface. Okay, and that will change as the bolus comes by and then moves on. Okay, but that is the driving force to drive material into the pores. So we have an effective CP star inside the pores. And the particle itself has a porosity, we'll call that epsilon sub p. Okay, so think of that in terms of the volume of the particle. A certain amount of that volume is porous to the mobile phase, so it allows the mobile phase in. It'll saturate that pore, but movement of material into and out of that pore, which always remains saturated with mobile phase, okay, the movement in and out for the analyte depends purely on diffusion. There's no other way in. Okay, so if we write a mass balance, let's look at the non-porous case first. If the particle is not porous, we only have to worry about diffusion, about mass transport to the surface of the particle, and once it gets there, there's nothing going on inside the particle. Okay, there's no diffusion into the particle. In that case, E sub p, the porosity of the particle, goes to 0 because there's no volume inside the particle, and this derivative of the internal one, C sub p star, goes to 0, so the derivative with time is 0. Okay. If we have a porous particle, which is most of the time in chromatography, then we have to deal with the concentration inside, the temporal concentration inside, the temporal change in concentration at the surface, and then diffusion into and out of the pore in the radial direction R. Okay, so that's our model for a porous particle. That's the most general case. All right, we can do the same kind of dimensional analysis. the initial bolus concentration in the bulk, okay, we'll call that C0 of any component I. That's what we put in to the column. That's the highest it will ever be. So everything at the highest it could be is of any of the other concentrations that we've described here, the highest they could be is the initial concentration. They always have to be lower than that. So we'll call little c sub bulk, c sub b, of any component is the ratio of the bulk concentration at any position in time to its initial concentration. We'll use the same initial concentration to scale the feed concentration, because that starts, the maximum it can be is C0, and then it'll drop off from there. It's usually 1 or 0, or little c sub f is usually either 1 or 0. The concentration at the surface of the particle, okay, is sometimes will be higher than the bulk, but it's never higher than CZ0. Okay, the concentration inside the pores of the particle, again, they can be higher than the bulk, because remember, it can diffuse back out once the bolus moves by, but it can never be higher than CZ0. So all of these are bound by the range 0 to 1. We can define our dimensionless time constant the same way we did before, okay? But now what we're saying is the velocity is the interstitial velocity, not the maximum velocity. The length is still the length of the column, okay, the length of that entire pipe filled with packing. So we can define a dimensionless time. We can define dimensionless distances, okay. We'll let eta be the radius of the particle. Remember, we've changed from the radius of the capillary to the radius of the particle. That's our surface area for adsorption. So it's the radius, which starts at 0, goes out to r sub p. So it's between 0, eta is between 0 and 1. And lambda is just length down the column like it was before. So it starts at 0, goes to L, lambda goes from 0 to 1. So we're doing a dimensional analysis, plug that in, and we find we can rewrite these models. There's actually 2 here. They have to be solved simultaneously. Okay, so we have, this is our model for the bulk material moving through the capillary. And in dimensionless terms, this gives us some dimensionless numbers come out of this. Okay, and this is our model for the pores of the packing. And we've got to solve both of these simultaneously in order to solve the problem. So that generates a number of initial and boundary conditions. So our initial condition, we have the concentration in the bulk, which we have to specify at time equals 0, concentration in at the surface of the particle specified at time equals 0. Okay, and we're going to treat things a little bit differently here. We're going to bring the analyte in the feed. So we're going to start off with a clean column. So we'll just define it as 0 throughout the column initially. Okay, so for our boundary conditions, we have two boundary conditions for lambda, and we have the inlet boundary condition, which CB is 0 until we have a feed coming in, okay, and then it goes up, and then the feed drops back down to 0. So we can specify this boundary condition for the dimensionless concentration in the bulk as a function at lambda equals 0. And we can specify at lambda equals 1, we can specify that this has to go to 0. All right. And for eta, here we have eta squared. Okay, so we have 2 boundary conditions for eta. Now remember, eta is diffusion into and out of the pores. And so for eta equals 0, which is the center of the bead, we have to have the symmetry boundary condition, because we're not having any transport all the way through the bead. It can only go into the center and back out. So at the center, this concentration gradient is 0. And at the surface, we get this equation. Now, I said we will now define the feed coming in for some period of time with its full initial concentration, and then after that it goes back to 0. So we start off with an empty capillary. There's nothing in the bulk, there's nothing in the beads. We inject a plug for a short period of time and at a uniform initial concentration, and then the feed goes back to mobile phase only after a certain period of time. Okay, so that's our square wave pulse in, and then we can model what happens as it moves down through the capillary. Okay, now in this model, since we've made it dimensionless, we've pulled all the parameters into 4 different dimensionless groups. One of these is the Peclet number. One of these is the Biot number. These are known engineering dimensionless terms. We're going to define those in the next slide. And then we have what's unique to chromatography is gamma and chi. Okay, gamma and chi are unique chromatography dimensionless numbers. So the Peclet number is a measure of axial dispersion. So it's how much we'll get axial diffusion over the time the material resides in the column. The velocity times the length is the it's L squared per unit time. Diffusion is L squared per unit time. So Peclet number is a dimensionless number. It's the ratio of axial convection to diffusion rates. So it's our band broadening as it diffuses axially in the column. Okay, the Biot number is the ratio of mass transport to the surface of the bead versus the particle diffusion rates in the bead. Okay, so once stuff gets to the bead, it's got to diffuse in and then it's got to diffuse back out. Okay, so that's what the Biot number represents. It's that ratio, rate of transport to, rate of diffusion in and out. All right, so we introduce the gamma number. The gamma number is the ratio of axial convection to particle diffusion, time constants. Okay, so we've got how fast is it? Think of, this is very similar to that dimensionless number for capillary chromatography. It's the ratio of how much is it convecting down the column with the mobile phase, how much advective flow are we getting, versus how rapidly it's diffusing in and out of the particles, or into the particle surface and back out, or in and out of the particles. And then we have the chi number. The chi number is basically a combination of the Biot number and the gamma number, so it's not really a number in and of itself. However, we have to adapt that for the bed porosity, which is what this add-on term is. All right. The key, though, is we've defined the chromatography model in dimensionless terms. It doesn't matter how big the column is. It doesn't matter how fast we're flowing down the column. Okay, it doesn't matter sort of what the mobile phase is, because we've taken diffusivities out of it, so it doesn't matter what the diffusion is. If we can keep these numbers constant as we scale up from laboratory scale to commercial scale, we should get effectively the same separation that we got at the laboratory scale. All right, so that's why we went through this exercise. We're going to see that in a minute. One of the things I want to go back to, however, is in this model we have this axial diffusion term. Now, we didn't drop it out of this model. We dropped it out of the capillary chromatography model because we said R was much less than L. Therefore, R over L squared is a tiny, tiny, tiny number. Well, the Peclet number, if that is a large number, 1 over the Peclet number makes this term go to 0, or makes this term negligible compared to everything else. So as long as the Peclet number is large, like 1,000 or higher, remember it's dimensionless, as long as it's large, then we don't really have to worry about axial dispersion, and we can drop this term out of our model. Okay, so in reality, the three terms that really matter are the Biot number, maintaining constant Biot number, constant gamma number, and constant epsilon number. All right. So, as I've done in previous lectures and in the book, I've put together a spreadsheet to make things easier to do, so you can actually optimize and scale up, and see how should I design a column given this condition that's working at the laboratory. How can I scale that up? Okay, or how can I mimic in the plant, mimic in the lab what I'm seeing in the plant? Okay, let me go to that spreadsheet. This is available on the website. It's a resource to go with the book. How to use this is described in the book. There's some examples. Let's just look at this kind of quickly. As I mentioned earlier in the lecture, L over D is kind of important. You really want to keep that kind of greater than about 10 to 1. And that's simply because it's very hard to get uniformity of the flow as our diameter gets very big. Okay, so the longer the length, the more forgiving it is of the diameter of the column, but normally you try to keep about a 10 to 1 ratio of L over D. The pressure drop through the column is always a concern. Because we've packed the column with small beads, kind of no matter how big that cross section is, at some point we just can't pump things through. We got a limit on the pump, or we have a limit on the materials of construction of the column. Laboratory scale, that's easy to deal with because you can go with really, really thick, heavy metal columns. But when you get out into a plant setting, the diameters are so big that if you try to do a big pressure drop through a column, you'll just burst the column, and it doesn't work. So pressure drop we always have to be concerned about, and we have two equations that we can fall back on: the Cozy-Kármán equation and the Aragon equation. These are described in the book, and the constraints around these are Reynolds number, particle Reynolds numbers. The Aragon equation go a little bit further in particle Reynolds number than the Cozy-Kármán equation, but they're both essentially equal within the sphericity factor of the particles themselves. They're essentially give you the same values. Those are calculated for you here. If you want to look them up, that's there. Now we also have a constraint that the uniform packing of spherical beads, of perfectly uniform spherical beads, is 0.382. That's the best packing you could ever get. That's the best porosity. That's the minimum porosity that you could reach. Furness proved this in 1993. Okay, so you can never really get a lower bed porosity than that. And in most cases, you're really about 0.4, 0.45, somewhere between about 0.4 to 0.5, in that range. That's kind of normal for chromatography. In this case, in laboratory cases, they do a pretty good job of packing columns, so you can get pretty close to that. The particle diameter has an effect on things, because the smaller the particles, the smaller the interstices, the smaller R is effectively for our capillaries through that, and the higher the pressure drop. So here we have, I've set up a laboratory condition, a 5 centimeter column, 0.375 centimeters in diameter, inner diameter, and the radius of the particles are 0.75, so they're 0.75 millimeter particles. So that's a pretty small particle. The porosity of the bed versus the porosity of the particle. Okay, the porosity of the bed I'm saying is pretty close to its minimum, because it's I'm buying this column from a supplier, and the packing itself is about 45% porous. Okay, now I have to plug in values for my analyte, and my mobile phase. Let's say my laboratory was running at 1 mil per minute. With that porosity, I can calculate what the interstitial velocity is, V sub B. I can calculate from that, I can calculate particle Reynolds number, I can calculate pressure drops per unit length. That's what these two equations give me. With this sphericity factor, since this was, I could actually make these two agree if I picked the right sphericity factor. With all of these parameters that I've got for my column, I've got for my flow rate, I know this separation worked, okay, at the laboratory scale. Now, that gives me a Peclet number. Notice this Peclet number is really large. It's way over 1,000. So 1 over the Peclet number is negligibly small, which means I don't really have to worry about axial diffusion. Okay, and then I've got a Biot number, a gamma number, and a chi number. I have to worry about all 4 of those. I can copy these and put them as my target values for scaling up this separation. Okay, my pressure drop is fine, my L over D is fine, okay, and I've set in constraints for my optimization here. So since my Peclet number is so large, I'm not going to worry about that in terms of the sum of squared errors that I'm trying to minimize. I'm going to take that out of this operation, but I'll double check it at the end. So let's say I want to scale up 250-fold. Big scale up. So I want to go from 1 mil a minute to 250 mils a minute. And now I can't really get there because my pressure drop would be way too big. My L over D is fine because I can't do that through this analytical column. But I can set up an optimization. So if I go to solver, I can say set this sum of squared errors here, which is these 3 liquid chromatography dimensionless numbers, that's these, within the constraints of L over D being greater than 10 and pressure drop being less than 35 bar. Okay, that's those are my 2 constraints, and I'm going to vary the length and diameter of the capillary to get there. Now I'm using the same packing here. Okay, sometimes it's not possible to use the same packing, and you may have to play with that. You pick packing with the same surface chemistry, but it could be a larger diameter, it could be a smaller diameter. Okay, it's typically a larger diameter. It may have different porosity factors, it may pack differently. You have to get all that information from the supplier. But if I solve this, okay, it will try to match those, the Biot number, the gamma number, and the chi number. It'll try to match those as close as it can by changing the length and diameter of the column that we're using. And this takes a little time because it's bucking up against the constraints, it's bucking up against the L over D constraint, and it's still exceeding the pressure drop constraint here. But you can see the column's getting longer and the column diameter is going up during the optimization. Takes a little time. And our sum of squared error for the difference between the Biot, gamma, and chi numbers is dropping. Now if you notice, the Peclet number is still very large. Okay, even though I'm getting a longer column and a wider column, Peclet number is getting very large. So I still don't really have to worry about axial diffusion in this. I'm getting closer. And there we have a solution. So this is telling me the closest that I could match, and it matches reasonably close. It's a little off on the gamma number. I might want to go back and think about that a little bit, see what I can play with to improve it, but it's basically saying about a 2¼ meter column and about 0.2 meters in diameter with the same packing material that should allow me to scale up to 250-fold. Okay, I haven't changed any of the packing material. I can go in and do that, and I can still try to match these numbers. So let's say I wanted to go to a 1 millimeter packing. So I'm going to make the pattern from 0.75 to 1. So that would be 1e minus 3 centimeters. Okay, that will lower my pressure drop tremendously. And if I run the solver again, now again, I've assumed the same porosity. That because it's a bigger particle, it may have a different porosity within the particle. It may pack differently in the column, so you have to worry about that. The packing manufacturer will tell you that information. Okay, but here I've gotten a lot closer to my values, and I'm still well within the constraints, but I only had to increase the column length a little bit from 2.25 up to 2.81 meters, and but the diameter is a little bit better at roughly a quarter of a meter in diameter. Okay, so it's possible to run this with different variations of things based on what you can find with packing you can find with the same chemistry and how well you can pack those larger columns. So this spreadsheet I use a lot for scaling up in chromatography. You obviously start with a condition that a chemist has worked out in the lab, and then you want to transfer that to the plant. This is a convenient way to do that. All you need is a little bit of information about things that are usually ready available from the suppliers. All right, to our presentation, and I've shown you this LC parameters and numbers. Again, it's available on the website. Please buy the book. The book will cover a lot more of the derivations. It'll cover more information about different types of chromatography and how to apply this to different types of chromatography. You can see links to both the LC parameters and numbers spreadsheet, which is a resource for the book, and where to purchase the book at www.bioseparationstext.com. Thank you.